Okay. So this also they are now trying to implement like I think they have already done, I think so. These are the only instructions that are required for the RV32I specification. So they have explained what are these instructions are about also. So I don't have to go into details about that. So I want to mention that I have one like Python based single cycle emulator for the this RV32I. So just wanted to show you like how the code look like for that. So it will look like if you look at the code, it's very simple to understand. Also at the end, like at the end of line, like if you look at the line, it's only around 333 lines of Python code that is implemented all these 40 instructions. So the thing is like what we can do with this only 40 instructions. That's the question. So to see what we can do, let me open a code. So if you guys are familiar with C program, this is a simple this is a simple C written program to print hello world. So in addition to that, I added two floating point values and put the operation, and the output is also printed with this. So I'm going to run the I'm going to run this. I want to compile and run this on my emulator and see. So the calculation is coming. So by implementing a 333 lines of code in Python, we have a processor that we can run any C code. We can compile any C code and run. So that's simple. riscv is at a basic level. So it's so I hope you guys have an idea on that. So you can get this from this. I will share the link to the group. Link in the group. You can get this from this address. You can either choose to look at the code, or you can try to implement your own Python code before you can start implementing Chisel or Verilog based implementation. Or if you want to start with the Verilog implementation, if you can look at the code, it would be good, I think. So before I talk about the Shrimpa, I will talk about our final year project. So in 2017, we did the final year project. So the task was to implement a riscv based 32-bit processor implementation. So like this was the project was not given to us directly. Like this was given to our previous batch. So they have decided how the architecture will look like. So I think like you guys must have some idea about what is pipeline. So I don't want to go into too much technical details of this. So it consists of 12-stage pipeline. This is a 32-bit implementation, and our instruction caches is like directly addressing the memory using AXI interfaces, and also the data cache also address the memory using the AXI interface. And there is a peripheral interface bypassing the cache to interact with the peripherals of the processor. That means something like UART, VGA, and all. Like we can use that peripheral interface to interact with the the peripheral in the SoC. And other than that, like there is something called branch predictor that to address the hazards that are introduced in the pipelining, like that is control hazards. Like what happened when we only see where's the branch. We assume that the next instruction going to be executed is going to be the next program counter, that is PC+4, and we start pushing things into the pipeline until we get into the execution stage. At the execution stage only, we know that there is going to be a branch. So after that, the instruction in the forward stage is not valid, because we need some other PC, but the instruction is about to execute is from some other about to execute is next PC, but we need some other PC. So what we need to do is we need to discard all this. We need to flush the pipeline, and we need to inform the next PC predictor to fetch this PC instead of PC+4. So it takes 1, 2, 3, 4, 5, 6, 7 cycle lost because of that. So what branch predictor does is it will kind of try to predict that whether to increment the PC by 4 or whether there is going to be branch in that particular particular PC, like for the next PC, whether this is a branch instruction where it's going to jump to some other PC, or shall we implement the PC by 4. So that part is implemented in this. So other than that, there is this forwarding unit that is because, like, let's say the output of these calculations will be written after the execution stage. It will go through data memory 1, data memory 2 and 3, data memory 2, 3, and write back stage. After the write back stage, only the value will be written into the register array. So what if the next instruction is needing the value that is calculated out of the execution unit? So what can we do for that? So for that only we introduce something called forwarding, where we pull these values from the pipeline stages and mux it and select that mux to give the value to ALU instead of the value read from reg array. So that is a basic idea regarding this implementation. So like we implemented it in FPGA, and we were able to load any program into the RAM and show it to the demonstrated it. So after that, then we after we finished the final year project, we wanted to we didn't feel complete, because the ultimate task of the project is to have a processor that will boot Linux. When you have something that boot Linux, that means there will be millions of instructions with different combination will be executed. So there won't be we can show our design is 100% bug free, and also we will have a complete understanding of the riscv ISA. So in order to do that, so after we graduating, while working at Synopsys, we started working on a 64-bit version of the same processor. So we converted the 32-bit version of the processor into a 64-bit version. So there are some additional things needed for a Linux operating system to previous implementation can only execute any bare metal C program. We need to write all the libraries. So Linux means it's an operating system which gives the user program an environment. So that requires some additional implementation. So the caches requires virtual memory support, and also there will be a lot of we need to implement the privilege ISA specification where there are something called context switching will be happening. The context, basic idea of what is context switching is there will be permissions to access, let's say we are using WhatsApp and some other Chrome or something. So some JavaScript running in the Chrome cannot access the data what is coming to the WhatsApp or something. So the operating system should take care of it. So there are privilege levels in which programs execute. So there is something called machine mode where the normal initial BIOS, if you guys are familiar with BIOS, will be loaded and executed. Then the BIOS will copy the operating system kernel to the RAM, and it will execute. Then it will start the operating system kernel at supervisor mode. That means the second level. So and then the supervisor mode, it will in the supervisor mode, it will run the user programs that will run at the user mode. So some user mode programs, if the context is user mode, that is the least privilege, and some of the memory location won't be accessed. So that it will be blocked by it will create faults, and it will go to the operating system routine. So you may be familiar with seeing some of the access fault and segmentation fault from the some programs when you are trying to access some when you didn't declare a variable and do a memory allocation for that and try to access the variable, you may see some some access fault or page fault or something you will see. The reason is the operating system haven't not given the permission to the access those memory locations. So that is the basic idea of context, the privileges. So So we have implemented that also, and the rest of the things are pretty much the same with the 32-bit architecture. But we converted the 32-bit architecture into a 64-bit version, and it supports integer and multiplication and atomic operations. So that is about the SIGRiscv architecture and the SOC. So this is how the SOC looks like. So here we have the I don't know whether you have worked with microblaze or something. This is something similar to microblaze. So here we have the riscv processor, which is connected to the RAM through Axie interconnect. So this interface is for instruction cache accesses, and this interface is for data cache accesses. And there is the peripheral interface that is going to the peripheral. So right now, only peripheral that is supported is UART. So so you guys might have worked with UART also, I think so. So that is to show us a basic console to interact with the processor. And that means take the user input and print the output. So that is the only peripheral that is supported. As for how it is working, so like we don't have a bootloader program that is implemented or something inside the processor. So basically what we are doing is we just copy the Linux kernel into the RAM by the processing system that is inside the SIGFPGA, and then start the processor by releasing the reset. Then the processor will start running. So that is the basic structure of the SOC. And we did some benchmarks on the set board. So the thing is like there is something called Rocket Core that is implemented by the Berkeley people, and we have our SIGRiscv. So we did some dry stone benchmark on it, and our one scores around 1.4 DMIS per megahertz, and that means dry stone million instructions per second per megahertz. So and the Rocket implementation has 1.72 megahertz. But we are winning by the frequency. Like we have around 100 megahertz support at the set board compared to 50 megahertz support for in the set board by the Rocket Core. So if you multiply this by this will be around 150, and this will be around 86 or something. So we are around 50-60% faster than dry stone, like the Rocket implementation. So I wanted to show you this is how it looks in the Vivado. So we synthesize and implement this, and we can load the software development kit for that. And there is this SDK where we have the code to copy the I have the operating system kernel is in the SD card. So there is a code that is loaded to the sync processor to copy the operating system kernel from the SD card to the memory and to start the processor. So it already ran, and I have the serial terminal that is that is showing after booting the operating system. So you can see, like if you have worked with Raspberry Pi or something, you can see such printing from the kernel. I think from Ubuntu we cannot say these things, but so this is basically the operating system booting routine, and then this is the login prompt, and we input the credential, and now we have loaded this. So this is a full operating system. Like we can do whatever we can do in Linux operating systems. Like we can do ls. So we can see the list of files. And let's say if you want to open a text editor or something, like there is something called Vim, if you have familiar with this. So let's say we open a Vim. So so now we have a text editor. So we can write a code here. And you know how to save it. So after that, we can run it using and it is printing the hello world. So also, like if you want to change this file to the execution mode, you cannot directly run this file. This is not an executable file right now. So if you want to convert this file to executable file, there is something called chmod, change mode +x hello world.sh. So then you can run this file directly in the bash. Also, this also support Python. So you can I have a couple of scripts written for the Python. So there is something called hello world.py. So you should be familiar with Python also. So this is to print the hello world. So we can run this. So it's printing hello world. So there's a small game also written that is also written in Python to run Snake. So you can see how it is performing. So the delay is due to the bottleneck of the UART. So as you can see, it's running the game also. So other than that, let's say we open a text editor, and you can minimize the Vim by using Control Z. Now this is running in the background. So if you want to open it, like it will like, if you can resume the task also, you can also open the task manager and see what are the tasks that are running. So here it is showing the CPU usage and everything. And also like you can top and see what are the tasks we have minimized. You can like you can do PS and see what are the tasks you have run. So there is something called test. You can kill the process by using kill. So you just, so now the process is killed, so we cannot open it. So I think so I wanted to do a session regarding this. I mean, how if you guys have a set board with you guys, so set board or Cybo C720 or something with you. So I think I can do a session to how to like set up this SOC and how to run this SDK to get this Linux terminal and to interact. So you can do your own interactions and see what's going on. And also like we need to improve this SOC. So right now we only support like UART only, like only one peripheral is supported. So so the device driver is like, the thing is Linux already have all the device drivers for all the peripherals inside the FPGA. So we don't need to worry about the device drivers. We need to implement something called platform level interrupt controller to manage the interrupt that is coming from the peripheral and tell it to the processor, and processor will read the platform level interrupt controller to see which of the peripheral has generated the interrupt. You can see the interrupt signals coming from this. We need to connect it to the platform level interrupt controller, and the platform level interrupt controller output will be going to the our like interrupt signals of the processor. Like there will be one output coming. So we need to implement that. So other than so if we implement that and if we are successful, so also we need to specify the address of the each peripheral, like memory address of the each peripheral in a device tree, something called device tree. And the Linux kernel will take care with its driver reading, like initiating the peripheral and all. So if we do that, we can give that to our processor. Right now our processor doesn't have internet connection, so we can give the internet connection support to our processor. And also we can give something like, we can interface this USB. There is something called USB also. So if we can interface USB, we can connect keyboard and mouse instead of interacting with UART. And also if we can interface the HDMI, we can like get the user interface also. Like then we can show it like we can like, this is the first processor that is capable of booting Linux from Sri Lanka. So so if we implement the peripherals and all, we can show it as a complete computer that we built from the scratch. So that is a very interesting piece of work. If someone of you like willing to contribute, you can contact me. And also like from the architecture wise also, there are like currently the instructions per cycle is around 0.7 instructions per second. So we need to improve that further. Even though we are good at frequency, we need to increase the we need to increase the instructions per cycle. For that we need to cut down, like 12 cycle is too much. We can cut down some of the cycles, then we can we can eliminate the penalties of branch min prediction and all. Currently, we need to wait for 7 cycles at branch misprediction and all. So we need to cut down some of the cycles and all. So, and also we can convert, like we can make this address translation parallel to the cache. So such that there will be two pipeline stages will be lost. So that is called virtually indexed, physically tagged cache implementation. So there are a lot of work to be done in the architecture side also, and there is some work to be done with the peripheral that can be done immediately like that. That can be done in the foreseeable future. Architecture improvements will take time. Also, like we can start on implementing a 32-bit version of a processor that is comparable to the microblaze. This implementation is both compatible with the ASIC and FPGA. So we need to have some implementation that is more FPGA specific, which can be used instead of microblaze, where we utilize all the IPs inside the FPGA, and we can achieve around frequencies like 200 and all. Then it will be a work for a good paper also if we can implement that. And we need to get the 32-bit version Linux working also. We couldn't compile the 32-bit version of the Linux kernel also. If somebody can look into that and we can start implementing a 32-bit version of processor also, that will be another part of work we can look at. That is from the architecture side. I think that's all from my end. Any questions?
Excuse me.
Sorry.
No question.
Yeah.
I was wondering whether how do you like control the signals in a pipeline processor? So in a single cycle one, it's obvious how to control a control store, but in this one, how do you dispatch the control signals?
The control signal is like it's generated from the instruction decoder and it's propagated along the pipeline with the signals. Like we copy the value to this at this stage and this stage, and the controls will be flowing in a row, something like that.
And another thing, so is this architecture scalable, let's say, to 4 cores?
Yeah, that one I missed. Like we need to implement the cache. We need to implement the caches to support coherency. So if we implement the caches, to support coherency, then we can go multi-cores also. That will be another interesting piece of work. So there's something called MESI protocol which we can implement. So currently we don't have the support. Caches don't support coherency. So I forgot to mention that part.
Thank you.
Any other questions? If there's no other question, that's all from my end.
Now, just in the answers of other questions, let me just try to highlight something. I think probably you might not be able to see the sort of impact this particular project has created, and also like what exactly this really means. Now, what you've just seen is basically Linux running on a processor that was created by this group. Okay? And Linux being completely independent and actually is complete outside operating system. That's an acid test. Anything that I mean, if you really want to actually test your processor that you design in the maximum possible way, that's running Linux, because it's a complete operating system, and the fact that actually it is able to run without any issue shows that your architecture is correct and your implementation is really bug free. So if you really want to test like a digital system, or like in a processor in this particular instance, exhaustively, then this is the best way to do that. Get a general purpose application and run on that one. So the running operating system, and basically within the operating system, you can actually run any program, as Vidusan has actually demonstrated. running some basically text editor, and even running a game. All that means within the OS, all the applications are supported, and all these applications are also running quite well without any issue. Obviously, it's subject to some limitation of the implementation, but it shows that the current implementation is running well. So that, I think, probably you might not be able to really appreciate it right now, but that is the ultimate acid test for a digital system, to get something completely independent running on your system. And the fact that it's running actually shows everything is fine with the implementation. So this is ultimate verification. This is what I wanted to just highlight. Thank you, Vidusan, for I think there are a lot of